So I would like to talk about eBPF loaders. I'm going to do a little quiz beforehand. Anyone hands up for anyone who knows what a loader is? eBPF loader. All right. Who of you has written any eBPF? Doesn't matter in what capacity. Hands. All right. Then I have a sort of idea. So, all right. Let me start a little. Who am I? Thank you for introducing me. Thank you for inviting me here. My name is Reimerink. I work at Isovalent at Cisco. We add Cisco parts because we were recently acquired. I'm a cilium contributor, part of the loader team and a foundations team. So my day job is I do a lot with loaders and everything that comes with that. So I also do a lot with our loader library, cilium/eBPF on GitHub. And I maintain my own eBPF doc. So if you ever wonder what a certain eBPF term is or something like that, then you can likely find it at my docs. So the only plug I will do for now. So before we get into the belly of the beast, what is a loader? So when you create an eBPF program, so focusing on the diagram, you first have to you write it in some programming language. C or Rust is an option nowadays. You have to compile that to get some bytecode, and that is for C. We end up with basically always we end up with an ELF file, and then whenever you are ready to actually start using your eBPF program, you have to load it into the kernel. And that is typically done by either a dedicated program for the job. So the IP command or the TC and the TC command actually have functionality to do this loading for you. We have a BPF tool, and BPF trace actually does it dynamically creates its own programs and it loads them. But you can also write your own loader with a loader library like libbpf, which is probably familiar for some of you, or eBPF Go. IA is for Rust development, and BCC is for people who want to use Python. But BCC also does little dynamic compilation, etc. So the loader is the part that actually makes the syscall, and that does actually quite a lot that you wouldn't know if you only ever use it from an API perspective. So I have a very simple program. So it's an XDP program that just collects some flow information, so some bytes and packets for destination, source and destination address. And I couldn't fit it all on the page, so I have a little forward declaration there, but we'll get into that. So this is our C program, and then we compile it. So what I have here is any normal C programmers will know the above command. So just clang output something, and then we get an executable out of it. You give it permissions, you execute it, and it's hello world. But when we use the BPF equivalent command, which is a little longer, if we actually get a relocatable, that's because I didn't use because the way BPF works. And I can't just execute this. It will say, nope, no, not for you. Because in comparison, an executable is the pre-made closet on the right. But with BPF, we have the IKEA. We get the IKEA packet, and you have to do some assembly still, which is what our loader is for. So this ELF file looks something like this. So this is for my example program that I showed before. So we have the ELF header, which is at the top. So that is how our file command knows that it's an ELF. And then we have all of these sections, they are called. And every section has some unique form of information. So you can see that every section has a different format, and their formats are all based on convention, typically on the names or special flags that they have. So this is what we are presented with, or what the loader is presented with from a user. But what the kernel wants is this, the syscalls. So Oh, I seem to be missing a bit of the documentation. Anyway, so it's the man page of the man page for BPF, and this is basically the whole API from the kernel side. So what we have is we have a BPF Cisco, and the only thing you provided is you provided this very big attribute structure. And what you'll find is that it's a union. So and every command has its own field. So basically there are like a bunch of structures. Every command has its own fields that you want to provide. And that's how we communicate. There are actually 36 commands as of kernel 6.8. I believe they're not normally adding more, but you never know. So most of them are actually for like CRUD operations on maps. So maps for the non-initiated are the data structures where the kernel stores everything, or where eBPF programs store everything. But we can actually interact with those from user space as well to read what is there, to iterate over them, and do interesting, more advanced things like freezing them or binding them to specific programs. Of course, we need to load, attach, detach programs, which isn't always used. We'll get to that. We can run them, query for their existence. BTF, we'll get to what BTF is. Links, we'll also explain those. And some pinning and other operations. And like most of them are, again, for like querying, like listing whatever, which programs are currently loaded in the kernel and stuff like that. So these are normally, like every one of these are normally wrapped by some nice function in your programming language, but then the loader will translate these down to syscalls for you. So you can, in most libraries, like use them directly. For example, libbpf, or there might be like higher level APIs that just say, do something, and then it translates into like a bunch of these. So this is a Gamma program. And what you'll see in eBPF programs is that there's this sec macro on the top. And this tells the compiler to put this code into a specific ELF section. And this is an eBPF thing. People decided to use the section name to give hints to the compiler on where to load a program. So in this case, I say, because it starts with XTP, I'm telling the loader, hey, you should load this to. This is an XTP program, and then it will use that later on. And then we can inspect it. So I use LLVM object dump here to actually dump the contents of this. So we're going a little bit deeper already. And this is what we actually get out of our compiler. So it's a very regular pattern. Every BPF opcode is always 4 bytes? 8 bytes. We start with an opcode, so that's why it's in this very regular pattern, by the way. So we always have an opcode. We have source and destination registers for like moving things from register to register. We have an offset, which we use to jump to throw relatively within the code, and we have an immediate value, which is by default 32 bits. So to set some value in a register, like to an explicit value, but there's also this neat trick where sometimes we use 2 instructions together and we just do that to get a 64-bit number, so we then can combine the immediate values from two instructions. So this is like what we get, and this is this is like the almost the thing that we might want to give to the kernel, but we have to do something. So we can also, instead of just dumping the bytes, we can ask it to actually decompile this, and then we can see the instructions on the right. And what you'll notice is that there's this call instruction with a -1, and its source register is set to 1. But that's strange, right? Because there's no source for calling a function. And this is actually a hint to the loader that, hey, we need to do something here. This is where we're missing a bit. And the reason it's here is because I'm using I'm doing a function call. And in BPF nowadays, it's supported to do function calls. We call it BPF to BPF functions. But the loader needs to do a little bit of work to make that happen. So what happens is we had the instruction that was missed that had this -1. And then when we have the section which starts with .rel, it's the relocation entries for that section. And then at a certain byte offset, we have a relocation for our handle IPv4 function that we forward declarated. Now, if we look up the symbol table, then we can see that this symbol actually can be found in the .text section, which is where the compiler will normally put all of our executable code if we don't explicitly set a section on it. So all of our shared code, basically, not our entry points, but the other functions, if they're not inlines, they end up there. But when we look at all of the information we can provide to the kernel for our program, we only have one pointer for our instructions. So we need to assemble this. So let's say I had two programs and they shared some features. So this would be how it would look in our file. We have like some functions, we get our entry points, but then we actually need to assemble them into the following two things. So we need to figure out which functions are actually used, then make blobs of the code where the functions that are actually used are appended, and then we can resolve the relative addresses so we can relatively jump to these functions, and that's different. So this is something that a loader does for you whenever you use something like this. And actually similar thing happens with maps. So we define a map, we have the same thing where you have a key, a value, we define what it is. And here we have the same macro again, the sec macro. So what we do is instead of putting this in the default place, we put it specifically in .maps because .maps has significance for us. And the way it's used is that in the function, what I specifically would like you to look at, I didn't highlight in this case, but is the map lookup element. So here we have a pointer to this flow map, which was a globally defined thing. But then if we actually go look at the code, then this is an example of the 64-bit immediate, so where we use two instructions at the same time. And here should be the memory address of the map, but it's not there. And actually the reason it's 64 bits is because the kernel is going to, whenever we give this to the kernel, it's going to reuse the exact space here to put an actual 64-bit memory address there. But we don't have to bother. We don't have the memory addresses of where the actual map would live in kernel memory. But we have to provide it something. So what we again do is we go look, we have relocation entries for exactly these instruction points. Look up where is this in maps. Cool, that must mean that we need to put a file descriptor for a map here. So whenever you define a map within your code, it's not actually your code that is creating it or whatever, but it's a very indirect hint to the loader to create that map for you and link it to your program right before the program itself is loaded. Creating a map is also, again, its own opcode with a lot of info, with a lot of type information. And these are derived from whatever you put in there, like the map type is here is on the top and the size of your keys, but also some other things that I don't have time to explain all of them. So you would think, cool, so that information must be in the same way it's in or must be in that section then as well. And then you go look and it's 0. Why? Well, the reason is if you look at the struct is that this is actually the definition of the type, but we never assign any values to it. So everything is 0. Now, in the olden days of the very early version of eBPF, maps actually used to have this very specific struct definition, and you actually did provide values of the maps, and they would go in the maps section, not the .maps section. But this is deprecated, long not used anymore, and now we do it this way, and it's called BTF maps. So before I can explain then how we actually can use this information, I need to explain what BTF is. BTF is BPF type format, so it's like all of the type information. What does my structure look like? Is it a pointer? Is it a number? Whatever. Like all of the type information is in there. And the reason kernel developers decided to create this is because it's way smaller than dwarf information, which is like the default information that you would use for a debugger. But we still derive it from dwarf, so there's tooling that can turn all your normal compiler outputs into BTF and so on. Why do we need this? For a bunch of reasons. One of them is the maps. We have spin locks, callbacks, a lot of other advanced features where the kernel actually, for example, wants to look inside of the map to see that if you want to use spin locks on a map, it needs to make sure that it knows where in that map value you have a spin lock. Do you actually have a spin lock in there? So it uses this type information to do very strict validation also, so that you actually did what the compiler want, or what the kernel wants you to do. So it's just like providing additional information on top of just the bytecode. It also allows for flexible map attributes like we have. I'll explain it in a bit. It provides additional debug information and so on, and core, also deferred for later. But what is important to remember is that by default, for example, in Clang, you need to actually always compile with the -G, which means that it includes these debug symbols in there. So a lot of people at first get confused, like why doesn't this work? And they just forgot to add the debug symbols, and because it's not something you would have to do in non-eBPF programs. This BPF looks something like this when you inspect it. So there's a lot of information here. And what I would actually, so an actual focus of this is that we have a special data section .maps BTF, a bit of BTF information. Now BTF has so every type in there has a number, and they refer to each other. So we can actually rearrange this around this data section, and then we would get something like this. So we say, okay, we have a data section, .maps, and we have one map in there, which is one variable in this case. It's a global map, and it has this structure. And we actually, so there's this very rich type information about exactly what your key looks like. So you can have three structs deep, like keys that are 3 structs deep, or very, very complex, and it's all expressed here. And we use this to actually infer all of the things. And there are a few tricks that I can't go into the details, but for example here, we have the type ID, so the type of the map, and we actually encode with an array, which with a pointer to an array, we encode like literal integer values. So it's a little complex for the types, but for the constants. But for your actual type information of the keys, it makes a lot of sense. And all of this is also passed to the kernel, so the kernel will also have all of this information. BTF types, so there are a couple of types of them, of BTF types. It's a little complex. We don't have really great vocabulary, but so there are a few kinds of these types. All of the type information is the integer, everything is a number in the end, right? So everything is an integer, and then you can describe what kind of integer, make an array out of integers, make an array out of structs that will stack on top of each other. We have a few declarations, like is this a forward declaration? Is it a function? Is it global variable? Stuff like that. A few additional quantifiers, like is it volatile, constant, restricted? And we have a few tagging options, which are more advanced eBPF structures, but you can basically add annotations to your types, and then you can read them, for example, in user space to do interesting things. We have BTF, but there's also extended BTF, because we didn't think of it when we created BTF initially, apparently. It has this special structure, and what it has is func info, line info, and core relocations. And actually I'll go into these a little bit afterwards. But just know that they're there if you see it. And these are actually really useful, but they leverage the existing BTF thing. So if you have offsets in here, it actually references to offsets into the original BTF block. When we load this into the kernel, we actually only load this whole BTF blob that we get almost one-to-one. So there's really not a lot of work in this case needed. The only thing, only if you actually want to understand how it's packed, you need to do a few things. And then once we have loaded that BTF, we had all of these numbers, but these numbers it's technically optional, but nowadays you will always want to do it, provided as when you're loading the maps, you're telling the kernel, hey, this is the ID of the key type, this is the ID of the value type, and this is the file descriptor of the BTF. That's where you can find these IDs in. And the same goes when you load a program. So when you load a program, you say, hey, this is the BTF ID for my program, or this is the BTF ID where you can find a bunch of stuff about everything that's related to this program. And there's also the file, the func and line info. So the func info is for every function. There's one description, and it's like the line of the function, or how the function is called, and where it is, at which location it is. So this is something that we actually have to generate. So we have to when we make combine all of these functions together, we also have to make sure that these instruction offsets are good, and they're actually used for a lot of things. So BPF to BPF call validation, for example. So at some point, the kernel decided to do it out of order, so you can validate instructions or functions you call before the actual entry point. But to do that, you have to always make sure that you use the right amount of arguments, that they are correctly set. They're also used for callback functions and for a very interesting feature which is called freplace. Where you can replace global objects in the kernel. So you can actually replace an eBPF function with another eBPF function, and it gets really mad. But look it up afterwards, because you can do really interesting things with this. And the line info is the blue stuff you see. So whenever we dump our program and we load it, our program with line info, you can actually see parts of the source code together with your with the decompiled instructions. So it's really useful for mainly debugging to see so this is what is actually the eBPF bytecode that got generated from a certain line of code, for example. And the yellow bits are the func info, by the way. So these are so that's useful for readback. So what we actually end up with in ordering is something like this. So one ELF file can contain multiple programs and multiple maps, but only one BTF, and you always load the BTF first, so you can provide the file descriptors to the maps, and then you can provide the file descriptors of the maps to the programs. So you have a sort of ordering in which you can in which you need to load things to get it all to work. So the next thing I would like to dive into is something called core, which is really useful for anyone working with probing, K-probes. So if you don't really need this when you do network programs, but if you go inspect kernel internals, then this is very useful. And before I dive into what it is, how it works, is explain the problem. So let's say I have a K-probe and I installed it on TCP close, and I want to then record some very specific parameter. So in this case, I want to record the cookie counter. But it's actually nested quite deep in this kernel structure. So this would be how you might originally do it. So I read this from the kernel, and then I push it onto, in this case, a perf event buffer, which is basically just a one-way street where I can push events to user space. So this might work if you run this on exactly the same machine that you compiled it against. But the moment you compile this on your kernel in 5.9 or 5.19, whatever, and you try to run it on anything else, and this structure changed in any significant way, then this doesn't do what you think it does, because the compiler just translates all of these names into an offset. But that offset changes. So how do we deal with compiling our, so how do we fix this? Is we can use core, which stands for compile once, run anywhere, everywhere, sorry. There's this really good blog that explains, that goes in way more detail than I ever get on how to actually use this. But I wanted to like do a very brief overview of it. So there are these bunch of these macros where you can, so the most important one that we're going to look at today is this core read macro. But there are also a few other ones where you can, for example, say, hey, does this structure have a specific field, or does this enum value exist on the current kernel? And you can actually dynamically create logic that only executes on certain kernels under certain circumstances, etc. But actually, if you go look at how this works, it all boils down to a few of these compiler built-ins. So we extended the Clang compiler to understand these, and whenever it sees, I believe this is not extensive, by the way, but whenever it sees these built-ins, it actually generates these core relocation entries that I had shown before. So how do we use it? Is we just replace our helper function to read from the kernel with this macro, and instead of, and this is actually like an how do you call it? A variadic argument list. So we can put as many arguments in here as well as we want. The only thing to remember is that basically you replace your arrows with commas. It's just how this macro works. But what this macro does is it still generates the same. So on the right side in the comments, it's basically what this translates to. So we still use the same probe read kernel, but it generates a little bit more for us. It automatically adds the size of, etc. It returns the value, but it also inserts this built-in preserve access index built-in. And what this does is not much, so it still does basically the same thing. So if you, I'm going to walk you through this. So this is a translation of this is like the decompiled instructions. So the move instruction isn't important. On one we load X memory double width. So this is actually the loading of the sock pointer, the SK pointer, because reasons that I won't go over. And then from that socket pointer, we need to jump a bit down. In this case, 104 bytes to get to my counter. And that's all calculated based on how many fields are in between this counter and the head of the structure. But what we also have is a relocation entry, which exists. So what this relocation entry hints to us is that, let's say that I was accessing, I have some random structure and I was accessing field C, then it would encode 16-byte offset. But in our target, it is actually 24-byte offset because someone added a field in between there on this new kernel version. And what this relocation entry is going to tell us is the name of all of the structs, so it knows which fields we are referencing and which struct, how deep. And we have a little bit of magic, which is called VM Linux. I actually have that a little bit out of order. So VM Linux, this is a big blob. I will coordinate to make the slides available somewhere, but this is interesting for later. So this is a little bit of logic to actually use one of our CI kernels and extract the VM Linux bit out of it. VM Linux is the ELF file that actually is the Linux kernel. So it's like the Linux kernel in an ELF format. And it also has a .btf section with all of the types that this kernel has. So if we inspect it, this particular kernel has like 90,000 unique types in it. And we can actually read this. So when we load a program on a target, we read this VM Linux and we see, hey, we can see that there's this difference, that there's this field added. What we then do is it's all actually based on the name. So you have the name on the original one and the name on the new kernel. So when you do name changes, there is a possibility you can still make it work, but it's a little bit difficult. Again, referring to the guide on core that I mentioned earlier. But what happens is the loader like looks up all of the like every kernel that's named sock in this case, and it might be one, it might be multiple, depending on how good the kernel people are naming their structures. And then we actually have we find we go look in all of the structures, and we do a sort of game where we give them scores based on all of the relocation entries, and the destination type that we find that matches the best to the one that we knew, that's the one we're going to use. And if we end up finding a type that like is perfect for 90% of our relocations, but there's just one that wouldn't work, then we poison it. So we, if that instruction were to run, it actually crashes on the verifier. That sounds really dramatic, but you can actually use these conditional, so these questions you can ask as well, like does this field exist, to then make sure that that code that would call it is actually that code. So there are tricks, but it's a little bit advanced. But what I want you to remember is that the loader can use the BTF and the difference in BTF to do a bunch of these things, like know what the like change a byte offset, or change the value of an enum, or change actually even like how much you shift certain bits in a field before you use it. So when we actually, the slide I showed before was extracting the VM Linux out of basically a kernel ISO or a kernel image. But you can also, if enabled, you can access the BTF blob of your current VM Linux on this syskernel BTF VM Linux path. And when I ran it locally, I had a little more, like I had more types than in my CI environment. But it's all the same idea. And actually, if you go look in this directory, you'll see that every kernel module, or nowadays it should be every kernel module that's like compiled with your kernel, actually also has blobs of BTF. So you can also attach use core with functions and types that are not in the main kernel, but that are in some kernel module. The way you would use it is you can use this BTF tool, which is really great, to dump this file as well. Let's say dump it as C, and then you'll actually see that it will translate all of that BTF information back into C. So you can actually, when developing locally, you say, generate a VM Linux for my local machine. It gives you all of the types, and then you have access to all types. You never have to copy paste from kernel sources or whatever. Every data, every type that is available in the kernel, you can access that as well. So it's really convenient. So next, kfuncs. Kfuncs are cool. Kfuncs are basically the replacement for helpers. So when you start and you think you know helpers, then you also got to remember that you have to learn even more after that. We started since kernel 6.2, no more helpers are added, and the reason behind that is somewhat political, but it's just a reality. So after if you're looking for some functionality and you can't find it in a helper, go explore kernel for kfuncs. And basically what the idea is about kfuncs is they're actual functions of the kernel. So instead of writing special purpose kernel helpers, we can actually just designate an existing kernel function and say you're callable from eBPF now. But of course, we have to do some magic in the loader to make that work. It requires BTF, so there's a bunch of different ways or a bunch of different logic to apply here. Use BTF, and you can also use core-like logic to also check if these exist, for example, or not. So you can actually then query the pointer to a kfunc and see, is it null? If it's null, then it's not available on my current kernel, which is just possible. It looks something like this. So normally you get this from libbpf, I believe, but you can also define it. Anyway, what we do is we say, okay, we define this ksim attribute, And we put this, so any function with this, we should put in this .ksims section. And then we say, okay, these are external functions. So we define them as an external function, and they should live in the ksim. And what you literally do to use the kfunc is you have to know what the signature of the function is, and you have to include it and make sure that it matches the kfunc for the kernel you want to call it on. And then you can use it just like any function, any helper you would otherwise use. So then you thought, now I learned how the section attribute works. And we go look, and there's no .ksim section, and that's because, of course, everything is special. If we go look up, there's still a relocation entry, but if we go to this symbol, it says, yeah, it's undefined. It's in an undefined section. And that's because we need to look for it in the actual kernel code, right? We're referring to a kernel function, not to something that we provided. So what we then have to do is, so I dump, again, this is the BTF information for my program, and this is the function that I provided. So I basically provided the description of, I want to call this. And then it's up to the loader to go find that in the kernel and go find what that actually is. And in this case, I found it in the NF contract. So these K functions are not defined in the main VM Linux, but in this contract blob. And if you go look here, it is actually loaded as like the 108th BTF bit of information on my machine at the time. And I need both the ID, or I need to have this ID to load the BTF blob back in to get a file descriptor, and I need this number, the number of the BTF, the BTF number here. And what I then can do is there's this magic but it's this field called FD array. So I can provide an array of file descriptors, in this case the file descriptor of my module. And then I don't have a slide of this, I believe, no. So then in the code, we actually have a call instruction, just like I showed at the very beginning of the presentation. And in this case, instead of just putting the number or like putting a relative address there, I put the file descriptor or the index into the file descriptor array in the offset. And then in an immediate value, I put the ID of the BTF. And then the kernel knows, sure, you are calling like this specific function in this kernel module. And the verifier does a lot of magic, turns that into an actual callable memory address, etc. But we have to still like combine a lot of stuff. So we finally did like use every advanced function in eBPF, put everything together. We loaded our program, and now we need to attach it, right? Cool. How do we do that? Well, it depends, because nothing is easy. So we have sockets. So for socket filters, which are like, I believe, the very first program type, we of course attach it to a socket. And what do we use to attach it? We use an IO cuddle. So that's a different Cisco. And then it's attached to the socket. Whenever we close our program, our socket is no more, so our program also unloads automatically. With kprobes and uprobes, and they actually attach to a perf event. So like normally you have also trace points in the kernel, for example. These are existing places in the kernel, but in this case we first need to use the trace file system to actually tell the kernel where it should create a kprobe before we can actually attach to it. So we have to first create a new kprobe location, then open a perf event for that kprobe, and then attach the BTF to it via the IOCTL. So there's a lot of work involved, and then in this case, when you close your main program, it also magically goes away, but you might still want the kprobe there, right? And the whole reason for that is because the perf event, like whenever your file descriptor to the perf event goes away, it's also ref counted, it goes away, your program goes away. You can fix that, I'll get to that later. But it's different again. So we have TC and XTP programs. They use the TC and the IP command respectively, and then use netlink underneath to do the actual attachment, and they attach to these other kernel things. But then when I close my program, they don't go away, because even when my program closes, my TC and my QDisk still exists, or my netdef still exists, so the ref count is still there. So if there's really asymmetric behavior between like all of the different program types, and then at some point we decided, perhaps we should start using this attach and detach BPF command to make it a little easier, but you still need like to get all of these file descriptors to these weird objects that have like their own mechanisms again. And this is all hidden behind this loader. Like if you use a loader or use a loader library, loader will tend to do all of this for you. You can just say, attach it to this thing and then just figure out how. But there is hopefully like one solution, which is links. So the idea behind the link, which was added in 5.7, is that instead of having all of these weird APIs, let's just create one API to rule them all with an asterisk, which I'll get to. And then support was added gradually. But this is, so if you're running on newer kernels, you can just use these links, and they're really nice. And the cool thing about the links is the links, as long as a link exists, it holds a reference to both the attach point and the program itself. So you don't have to like do a bunch of things, and you can, and they're just a BPF object as well, just like a program, just like a map, just like a BTF blob. So it's the fourth one. It's reference counted, so as the moment no one knows about it anymore, it's automatically like collected and removed, and it's pinnable. And so pinning is one of the syscalls I mentioned at the beginning. You can actually take any of these BPF objects, and you can attach them to the file system, and then the files, as long as that fake file exists, it will hold on to a reference to a program or a link or map, whatever. But you can, and the links actually are like a layer above too. So the moment you can actually delete the link without deleting the program, and that detaches the program at that point. So it's technically a neater API. It also has additional features, so it has BPF cookies, which basically you can give every the same, so you can use one program, you load it once, attach it at like 20 places, and give every location its own unique number, so you can resolve at which actual attachment point something was called. So you can also, attach multiple, your program at multiple locations with one syscall, but you can also have, for example, for XTP, not for XTP, but for TC, we now have like a new API using the links, where you can actually have multiple programs attached on the same location in a neater way, in a way that was not possible before. But it's not all perfect, unfortunately. So here we get to the asterisks. So it's not the perfect API to rule them all, because struct ops. I won't go into details, but also look them up. They're really interesting. The ideas that you can like implement kernel logic with BPF programs, like schedulers or other algorithms and so on. But you still have to do a whole bunch of a whole song and dance with like the special BPF map type for specifically this program, and then linking it. K-probes and U-probes and trace probes still need a perf event, so we're not get rid of the perf event. The only thing is we get rid of the ioctl, so you still need to do some magic there. A bunch of programs are just not loved enough, so the kernel developers never decided to actually implement link support, like LWT programs or socket filters. Like apparently no one uses them, so why bother implementing stuff, is, I imagine, their thought process. And then in 6.3, someone had the brilliant idea to, after that, reinvent a new way to attach programs. So there's a way to implement HID drivers, so human interface devices, mouses, etc., in BPF. But in order to do it, so you first write it, you have to create a second program that is a syscall program, which is not to implement the syscall, but it can call syscalls. So you have like the second special program type that then acts in the kernel, uses a special k-func to attach the program, and it's total madness. And then it somehow creates a link in there and passes it back up. So where the job of loader libraries is not yet done to hide all of this stupid complexity from the users who just want the hit driver. We're getting pretty much to the end. So a lot of these, I've talked about a lot of features, and a lot of these were like introduced over time. So how do you know how to use X, Y, Z? So initial reaction would be use a kernel function, like a kernel version number, like, oh, it was added in 6.7, so why not check whatever the kernel reports? Because kernel lies. Well, not the kernel, but distros. So there are a bunch of these distributions that basically create backports and patches and a whole bunch of stuff, and then not update kernel versions because they are made by the kernel project, right? So especially, for example, the example that I'm very familiar with is RHEL. So there's RHEL 8.6, which is based on the 4.8 kernel, but it actually has like 5.4 BPF features. So you just can't rely on these version numbers. And actually also like an anecdote, I wasn't there to witness it, but apparently like 15 years ago, or like whatever years ago, whenever we switched from kernel 2.6 to 3, I believe, there apparently like user space everywhere used the kernel function, the kernel version number, and it broke like a lot of user space applications. So long story short, don't use kernel versions. It doesn't work. But what does then work is probing. So, and it actually is really stupid, but probing is literally try and see if it works. So whenever we, for example, cilium eBPF loads, like before it will actually load a program, it will actually then say, okay, you're trying to load like an XTP program, right? Or perhaps something more complex. So what it then does is it creates this XTP program that's basically empty. It just returns 1 or whatever. So it's like 2, 3 instructions. So it can't fail unless unless it's something to do with the program type. And then when that fails, it knows to report, hey buddy, you're running on a kernel version that doesn't support your XTP program, instead of it's some, so that's a way to eliminate that specifically that is the issue, instead of like one of your program itself. Because for the kernel just returns, oh no, talking too long. So anyway, the kernel just returns like an error code, like something went wrong, but it often doesn't tell you, or at least not in a programmatically very easy way to figure out what went wrong. So what we do is we attempt to like, for the most obvious things, we have probes, and then we can return nice error messages, but these probes are also available for you. So if you, for example, say, I know that I implemented some function that only exists on newer kernels, then you can call the probing functions that are provided by the library, ask the library, hey, is this there or not? And then in user space, make the decision, do I load my legacy eBPF program or my new eBPF program? Or you can even like go a step further and start modifying stuff there, or providing that information to your eBPF program via maps, so they can do it on runtime, for example. So that's just really useful if you ever get into issues with this. So probing together with core can basically resolve any compatibility issue you may have. And that's all I have to tell you for today. So are there any questions?